Yeah. Did you get a chance to go through the problem number 4 or 3?
No, I didn't. I had assignments, so I didn't get a chance.
Okay, so was it the part 2 of the previous assignment?
I still didn't do the assignments. I'm not sure. I
Oh,
was planning on doing it today. It's
oh,
due this Friday.
okay. So do you have any doubts on that?
No, based on what I've read, like the instructions, no.
Okay. How about linked list? Did you get comfort on writing the code?
Yeah, linked list, I think I'm okay with. I just want to go over double linked list because I'm not
Hmm.
so sure about that.
Okay. What questions do you have on the double linked list?
Um, just like how to figure out like what's the beginning and what's the end, and like that, pretty much like how it works.
Okay. You mean the fundamentals of the double linked list,
Yeah,
how different it from the single linked list. Okay,
yeah.
you can do it. But before we go, maybe 5 minutes, I would like to check your understanding of the circular single linked list. If you go through the problem, a last problem, let me share my screen. We can spend around 5 to 10 minutes on it and then uh,
Okay.
work on the real one. Yeah, this one. This is a problem statement. From this book anyway, I can give you a diagrammatic representation too while you are going through this problem statement. I think try to spend 2 to 3 minutes, like what are the options available? How would you able to do?
Why is the output C?
Uh, that's really interesting one. Input, if you see, node 1 is having value A, node 2 is having value B, node 3 is having value C, node 4, 5 are having distinct values. But if you see, node 5 dot next is again assigned to node 3. You understand?
Okay.
If I want me to draw it through a diagram, I don't know, like it's drawing and Google Docs is not a great place to draw. But let me bring it the same diagram from the book. Later, I will draw a better diagram, but this one will solve it. Yeah, this is the one. This is node A, B. Maybe I'll write down a little larger. If we see here, the output should be now E. This is A, B, C. Probably it is D, E, F, G, H, I, J, K, L. But ideally, instead of L, it is again colliding. This is the end node, but it is assigning back to one of the middle nodes. So in this example, it is E, but it is fourth node, so we can assign the last value to D. So it will give you D. That would resemble the image. So what you should remember from this problem statement is this node is creating a circle, right? D is creating a circle because it is repeating second time in the linked list at the very end. That is called circular linked list. Ideally, if it is a big circle, when this node is A, means the last element is pointing back to the first element. But if it is in middle, then it creates a circle like this.
Okay.
It is a mix of single linked list until D. After that, it has become a circular linked list. Now the interviewer is asking you to identify this node. How do you find that?
Wouldn't it just be like which element is repeated?
Exactly, you're right. How do you find that duplicate element? If you see problem 2, it is telling the same, right? But the challenge here is, can you write that 4-5 lines of code to find that repeated element?
I don't think so.
But your idea is correct.
Yeah.
There are many ways to find that duplication. One, using another list, which will keep inserting a node unless there is a new node repeating. That is easy way. But say like the list size is 1,000,000 elements, like Amazon orders or Google websites. How can Google identify this website is exactly copy paste of another website? Because the Google is having database of billions of web links. How can its algorithm easily find the duplicates rather than what? Creating another billions of websites index to compare, because that will take years of time to do for the server. Even if it is an advanced microprocessor, it still needs days to create another database of billions of web links and then crawl each to find duplicates. So what is the smartest solution? Maybe more improved than using additional memory. Think, because that simulation gives you a lot of knowledge. I think another 2 minutes, I can give you answers straightforward from the book, but we need to brainstorm on that. So think what other options you have available. Your solution approach is correct. A duplicate element, there is only one, assuming. So it is easy to find the duplicate, but without using additional memory, in the sense another linked list. or array, any such thing. If you use another one, the space complexity will be big O of n. We need to reduce that in the interview. Think
Oh,
for
like maybe like I today we were learning about like quick sorting, so I'm just kind of applying that. Like maybe like keep like a pivot element necessarily, and like if it matches, that would be the duplicate. But if it's not, you can just like scratch it maybe.
you're pretty close to the solution. Think that's what the author is saying here. N1 and N2. N1 and N2 are like one is pivot, one is, but in linked list, we can't use the pivot concept because we don't know where is the beginning and where is the end.
Okay.
But in array, you are very clear. Start, end, and the middle.
And
But
yeah,
in a circle, we don't know what is the end. To find the pivot, either see, pivot can be either beginning, middle, or the last element in a particular segment. But here we don't know what is beginning and end. But you are very close. That concept is called runner technique.
okay.
Here, runner technique. So think a little further, but you are pretty close to the solution.
Like maybe like storing the previous elements or like website links or whatever, but I feel like that might take up more memory.
Right. But the
Yeah.
solution will 100% would work. Storing in another memory and compare for a duplicate value when we are inserting the next one will definitely,
Yeah.
but the search cost is more, right? It will be out
Okay.
of storing the elements itself will take. What if the last element is this size is 1 million rather than 4 or 1 billion in the Google case? It's hard. But the solution is exactly good. You should present in the interviewer. This is easy technique
Okay.
and you have memory. That's why
Okay.
you can ask the interviewer what is the size of the list. If it is a pretty small, like 100 or 1000, maybe we can use another memory and then just compare for duplicate. But what if the size is larger? This is algorithm. You can go through and let me know whether it works or not. This is the solution.
Okay.
Optimized, I would say. So we are not using any new list or array. We are just using variables. So the space complexity will be single. The author is very restrictive. I wish I should have typed by then. Thanks to Google. You got it?
Mm.
FastPointer and SlowPointer. These are two runner. So it is same as pivots. Here you are having two kinds of pivots. Those two pivots should collide in a circle. How do you make your algorithm to collide? This is the one. If you explain, lots of questions will come, but I would like to make sure you understand it well. This is very beautiful problem. If you understand this, you will get almost complete control on linked list, singly linked list problems. You got it?
Mhm.
So fast pointer is at here.
Okay.
Slow pointer also at here, at A. Okay, let me explain with our example. This is the original list. Fast pointer is having A. Slow pointer is having A as the starting node. And fast pointer is moving with two nodes at a time. So it has moved from A to C. Okay. But the slow runner is going with one speed,
Once.
A to B, in the second iteration. In the third iteration, it is at E. Okay. But this one is at C. It is at G. This one at D. Unfortunately, they are not colliding at the first round. But definitely it will collide because it is inside a circle. Maybe they might take more rounds. So continue. Don't give up in the interview. But it is at E. This first round is missed, but still they will continue running. I will be coming from after I, it has to come back to D.
D.
Now this is at D. However, it is at F.
Mm.
Okay. So we still need to continue. Second round is also missed. But definitely we need to continue. We need to have that patience. After D, again, it comes back to F. But G to H. And then
So it never goes back to ABC.
it will never.
Okay.
Both will never. Because they are inside the circle.
Inside this.
They
Okay.
rotate. They rotate. So this is D. They keep rotating in this circle. Because there is no connectivity back to one line. Yeah.
Okay.
Good thought. But let's continue. F to H. They both have collided at H. What's the use?
Mhm.
There's no use, right? Because they need the starting point. Sorry. So once they have collided, it means they are now in the same page. Means they are inside the circle. They are inside the circle, but we are not sure whether they will be at the right element, starting point or other point. We don't know.
But the starting point is A, right?
D. I mean, starting
Okay.
point of the circle.
Of the circle. Okay.
Yeah. So this is D. But they have been collided. E, F, G, H. E, F, G, H. They are here now. Okay, because they have collided here. Now, how can we take them back to D? Because the answer is D, but how does our algorithm know that? Hey, H is not the starting point, but we are 100% sure that now both the pointers are inside the circle. So for that, what the solution algorithm is saying is, When they collide, this is the point. They have collided at H now. Move slow pointer to linked list head. What does it mean? The linked list head is what? A. This is the head, right? The head is A. So move the slow pointer back to A. After the collision, the slow pointer is back to A again. But the fast pointer
H.
this is exactly how you need to explain to the interviewer. And he will give you 30 to 45 minutes, mostly 30 minutes to explain this problem statement. Since we are learning for the first time, it is taking a while, but it is really worthwhile to get complete grip on the linked list. So where are we? So what the author is saying, when they collide, move slow pointer to linked list head, keep fast pointer where it is. So the fast pointer is at H, keep it the same. And the final step is move fast and slow pointers at a rate of 1 step. Let's continue and return the new collision point. Okay, this is the next step. So now move fast pointer from H to 1 step. So it is the starting point, H to I. But slow pointer also by 1 step, A to B. And I to J, B to C. You got it? Slow pointer is starting back from here and continue. Whereas the fast pointer is continuing the loop from H to D. They both are exactly 3 steps away from D. Fast pointer is 3 steps away from D, technically 2. Slow pointer is back here, and it is also 2 steps away from D. That's what author is saying. And continue by 1 step, which is again J to D, and this one also J to D. Now this is the second collision point, and it is the answer.
Okay. So this works for any size loop?
Yes.
Okay.
It works for any size loop. First collision point tells you why like this. After D, the number of steps slow pointer has moved are present inside the loop. So each time it is moving, it is closing closer to the collision point because it is inside the circle. That many steps closer to the collision points. Whereas the second fast runner, it is 2 steps away. Each time it is traveling 2 steps. It will be even much more closer to the second one. So if you calculate any size, slow runner is taking n steps. It means fast runner is taking 2n steps if it is n number of steps. Say like the size of this loop is 10. If slow runner takes 4 steps, fast runner would have taken 4 steps, 8 steps. When do they collide? We have continued the loop. If slow runner takes 6 steps, fast runner took 12. If it takes 7 steps, 14. 8 steps, 16. 9, 18. 18. So what does it mean? They are colliding at a point, fast runner is taking 2 rounds, but slow runner is taking within the first round itself. Okay. But still they have not collided because 18 means somewhere at eighth position or ninth position. And the slow runner means again ninth step, right? Ninth step. So they can be adjacent, they might not collide. Again continue until they collide. So maybe 12 steps, slow runner is here, fast runner has taken 24 steps. 20 is over, 4 is here. 13 steps, 26. And continue until they collide. At the very end, because see, fast runner has entered into the loop after 3 steps of slow runner, right? So 1, 2, 3. Once the slow runner has entered into the loop after 3 steps. These are the steps exactly they are missing each other. After, while entering into the loop. This is the reason why you have to, after the first collision, the collision point is exactly the same number of steps away from the number of steps starting from the list. This is very important step. When do you need to leave? Because we need to continue the double linked list as well, right?
Yeah, I think 3:10, 3:15, anytime is okay.
Okay. I'll directly, you can go through the book right away. You can search it in Google. Otherwise, if you get time, you can buy otherwise. Ideally,
Okay.
PDF can be available in Google, but recommended to buy also or maybe take it from library. That is also better choice for this book. But anyway, I'll give you. For now, I'll copy paste the reason when do they collide. Because we need to go to double linked list.
I can do until 3:20 because after that the room is booked for someone else.
Okay, no worries. 5 more minutes left, right?
Yeah.
Okay. So you can go through and try to understand. It is not a big deal. It's
Okay.
a very important point. That's it. That's why I put it here. If you have more doubts, we can chat or maybe we can discuss in next Monday, right? Next Monday.
Yeah.
But this is a very important point to explain to the interviewer. The programming is very easy. You just need to write 4 to 5 lines of code. That would solve, I think, not 4 to 5. A little while, but okay. I'll copy paste it from the Visual Studio. Anyway, let's go directly to the double linked list. See, how do you define? Because double linked lists are the fundamentals for trees data structure. That's why. So how would you define a node in linked list? It's node. It can be the structure or a class. And then node next. If it is integer, you need to use int data type, int data or value, whatever. And double linked list adds another pointer called previous. That's it.
Okay.
The reason, see that the difference between next and previous is straightforward. Next will, in the previous example, next will save the link to address of C. And C will save address of E. And it continues. So next will always save the next element starting address. But when you come to the previous will save starting value is null, but C will save A address.
Okay.
That's why it is called double linked list. If you want me to pictorially represent, this is the one. Got it.
Yeah.
And
So how do you know which way the linked list goes?
good question. The recommended way is from head to tail. That is, the head's previous is null. So the linked list begins with a null, which is the previous value of head, and ends with null, which is the next value of tail, J.
Mhm.
So it's still always better to go with head to tail, null to null. So the condition should be either head node's previous is null or the tail node's next is null. This is the ending point. This is the beginning point. Okay. Then why we need double memories, right? Like this. Why do we need? Because this will give you an option to go easily do move forward or backward. In the previous example, if it is a double linked list, I can easily identify, right? Whether so I can go through my runner technique. Still, I can take two nodes like pivot, quicksort, and take the end, the tail node or somewhere, and one node will search positive wave, like next element. One node will search in reverse wave, previous element. So the collision can be even easier. Okay. So a lot of advantages and flexibility is there for you to travel the linked list, like this document, either forward or backward way I can travel, right? So the reason is I can use double linked list here. And similarly, if you take browser history, I can go back, forward, because one is next node, one is previous node. So I can store the browser history in a double linked list to move our back and forth, easy to do. Make sense? So that's
Yeah.
the purpose. But starting point, here, see, I haven't opened any new website. That's why I cannot go next. But if I open another new website, then I can go back and forth. That's the advantage of using both the pointers. And the remaining all operations are same. Creating, inserting, deletion, they're all same. But deletion, search are very easy because of two nodes now. Sorting also makes life easy. Okay. Probably next session, we can take one more difficult interview problem using the double linked list to get you much more comfort. And then we will quickly go to stacks and queues. They are also dead easy if you know the concepts of double linked list well.
Okay.
Because double-ended queue or hash map, hash tree, and many data structures are based on double linked list. Okay, so we'll talk more of those on Monday. At least start with Monday, and Wednesday we can cover stacks and queues. How do you apply double linked list or single linked list to creates tags and queues. They are not different. They are same as linked list or array, but the names are different. That's it.
Okay.
Okay, cool. Rishita is same person, but Rishita school is or university is different person than at home. Same for stacks and queues.
Mm.
They are nothing but arrays and data structures, but with certain mindset.
Okay.
Okay, cool. Let's meet on Wednesday. Sorry,
Okay.
coming Monday. Yeah.
Monday. Yeah. Thank you.
Bye.